We're coming around to see what factor pairs can you make. We spent all year working on multiplication fluency as well as division fluency. Are there any other facts that you know that equal 18? Going into it, I identified a ton of misconceptions.
What can you do with that to make a rectangle?
7 here.
With the JARS routine, they're able to see the connections between the facts and be able to really think about what does it mean.
It really forced them to come back to some of the foundational, like you need to model your thinking and show how you know. I wonder how you could use your rectangle to help you find more facts.
Hey, tell me more.
The array jar routine is where we can assess and advance through explicit teaching. Okay, watch what Zelda does with his tiles. And through that, we can really see their thinking around like multiplication strategies, how they're using those to find area. So there's a lot of different standards that get covered within this one routine. All right, for our JARS lesson today, we have been investigating about factor pairs.
During the launch, we're just giving a big question for kids to think about.
So the question that we're going to investigate today in JARS, our guiding question today was, what are all the factor pairs you can make using all of the tiles in your jar? So once you make your rectangle and you go to represent that on your paper, make sure you're keeping track with your labeling. Sound good? Mm-hmm. All right. Lauren's getting started with her jar. Michael's getting started with his jar. During work time, students are using their tiles to build a rectangle. We tell them like build it, represent it, label it to show their thinking on that paper. And that's when we're able to walk around and really see what students are thinking. And that's where we start to confer and decide who we're going to pull for the discussion.
How can we use what you already made to make another rectangle? Because there's some more. So how can we use this?
We could use 4s.
Why did you say 4s?
There's like 4 right here. You could split it into like 4 and 4. But like,
okay, but then how can we make sure it's a rectangle? I feel like there's something about 4s, but can you make it a rectangle using 4? I'll come back and check in with you in a moment. A lot of times we are able to catch misconceptions, especially at the start. And so it's a great time to just like have a one-on-one check-in with students. Hey, I left you with the 4. What did you do?
I put 8 into 4 groups.
So what is the factor pair that you found?
8 and 4.
I had great conversations that come to mind. One with Lauren, who ended up sharing with the crew. Lauren specifically, she had showed 3 groups of 7 equals 24. So you said 4 groups of 6 is true. Is a rectangle that is 3 groups of 7 equal to 24? Did you use all 24 of your tiles? She knows she had 3 extras. And at first she wasn't recognizing, oh, these 3 extras need to go in my rectangle. What can you do with those tiles? If we need to use them in the rectangle, where could they go?
Could add them here.
Oh.
To make it 3 times 8.
To make it what?
3 times 8.
So does 3 times 7 make a rectangle that's 24?
No,
But what does?
3 times 8 equals 24.
So I asked her a couple questions, and then she was able to correct that misconception just through answering some of the questions that I prompted her with. You ready? I was thinking this one would work. She had a misconception on this one to start.
Yeah, we can have that and see if other people can pick up on that thought.
All right, 3rd grade, swoop those tiles into your jar, put your paper in the blue bin, and come have a seat in circle. After work time, students put their tiles away, they head back to circle so that all students can see what's going on. All right, Lauren, can you show us how you built that rectangle? Talk us through your thinking process.
Oh, well, I counted my tiles so I knew how many I had.
How many did you have?
I had 24.
Okay.
And as soon as I figured out that I had 24, I immediately knew that 6 times 4 equals 24, so I tried that out.
Did anyone else start by counting their tiles and then you thought of facts that you know? See, CJ did that, Asha did that. So, these are the factor pairs that Lauren created for a rectangle with an area of 24. What patterns or connections do you see between these factor pairs? If you have an idea, put a thumb on your knee. We're going to talk with a partner first, but I want to give you a second to think on your own. Sometimes they are raising hands. Sometimes it is the turn and talk.
Again, building on to CJ.
We use a lot of silent signals, so I was really pleased to see a lot of students wanting to build on or they were agreeing or disagreeing with what was being shared as well.
I disagree with you. I do not think they're the same thing because 6 and 4 are different than 8 times 3. They do have the same area.
I was really excited about our discussion. The way that they all were eager to build onto each other's thinking.
Lily, can you get us started?
Yeah. So I noticed that 3 plus 3 equals 6.
Having Lily be able to start the conversation with the connection, who often has a harder time joining in the conversation, I think her voice was lifted up in that and making sure it's an equitable experience for everybody.
Can someone build on and maybe clarify a little bit? Crosby.
4 was multiplied by 2.
Which is another way to say 4 is doubled, right?
And 6 was divided by 2.
6 was divided by 2 to get to what?
3.
Huh. I see Kat noticed the same thing.
How many of you are convinced that you could double one side and have the other side? Okay. Somebody who has their hand up, how can you convince the rest of us? What would it look like to have one side and double the other side to get the other factor pair? Zelda, you want to give it a try?
If you split it in half,
Zelda, how did you know that that was half of the rectangle?
I knew because 2 groups of 6 equals 12.
Okay, what are you going to do with those 2 halves to make them into a new rectangle?
Ooh, actually, Zelda, pause. Who can predict what Zelda is about to do?
When Zelda physically modeled having one side, I think that's where a lot of students, those light bulbs really went off and we were able to drive home the connections between factor pairs.
Galvin?
I think they'll take one half and put the 4 next to the other 4.
Okay, is that what you're going to do, Zelda? Okay, go ahead.
Show us. Students are really leading the conversation and we're pulling out ideas that we are hearing and things that we want to lift up for the whole crew, which then leads to the synthesis of the lesson where revoicing in student words, you're really able to drive home the big point for the day. Will it always be like this? Double one side, half the other. Turn to your same turn and talk partner. Tell them yes, no, maybe, I'm not sure, and why. Sometimes students don't say what you're hoping they might say. Taking the time to really plan and think through what am I listening for in those turn and talks? What is that one little nugget that even if they say half of it, we can take that half and hopefully we can run with that. Nora, what was that question that you asked?
Would it work with the number that couldn't be divided by 2?
What do we think? Okay, let's try it. I think some of the messiness is supported by creating a classroom where there is kind of this culture of grapple, and I think that comes from teachers modeling when they don't know that that's okay and that we can try things to figure it out together. Does this only work if your product can be divided by 2?
Yes.
You kind of ended the discussion with a question for them for next time. Students can test out, well, could I double and have my own factor pairs? And then hopefully getting to when is it actually true and when does it not apply?
Theo, what do you think? With this routine, it's naturally differentiated. Kids are able to build their thinking at a level that they can naturally be successful at and start coming up with really great creative strategies.